The input pins on the parallel interface can sense whether a voltage is 5 volts or ground. In other words, one of two voltage states can be sensed, 5 volts or 0 volts. Two of the three inputs for each axis grouping are internally connected to 5 volts through a resistive load, so when one of these inputs is disconnected from the outside world, it will always sense the 5 volt state. Since the signals are connected to a resistive load, a short circuit can be applied to ground without damaging the port. When shorted to ground, the input will sense the 0 volt state. These two inputs are typically used to sense the closure of end-of-travel limit switches. Index or LPT abruptly terminates motion control pulses when the limit input associated with the direction of motion on its axis is 0 volts. This means that motion in the positive direction for any axis will be arrested by grounding that axis's high limit switch input, and motion in the negative direction will be arrested by its low limit switch input. However, motion in the negative direction is permitted when the high limit input is grounded, and motion in the positive direction is permitted when the low limit input is grounded. Thus, software is able to recover from certain physical conditions that otherwise might cause a deadlock. Index or LPT's limit switch inputs are designed to be used to delimit operational boundaries and can serve a double purpose as a homing switch. They are not to be used as safety switches. The remaining input in each axis group, entitled auxiliary input, is not internally connected to a driving voltage, and when disconnected it can arbitrarily sense 5 volts or 0 volts at any time. In other words, unlike the limit switch inputs, it cannot reliably sense an open switch and must be connected to 5 volts or 0 volts in order to read these states reliably. For this reason, it does not fail safe if used for functions like a start switch input, since an accidental disconnect could cause the machine to start unexpectedly. The standard parallel port can set the voltage level of an output pin to either 5 volts or 0 volts. Index or LPT's reduced current and winding power commands are used to control the general purpose output pins entitled reduced current and winding power. These output pins can be used to control features corresponding to their names on certain translators, but most systems use these outputs for other things. When set to 5 volts, an output pin is capable of sourcing a very small amount of current. When set to 0 volts, the same output pin is capable of sinking a relatively larger amount of current. Parallel port outputs are ideal for controlling external devices that accept what is known as TTL inputs. The manufacturer of the translator used in parts 1 and 2 of this series has inputs specified as TTL compatible. Consequently, you can wire directly from the output of the parallel port to the input of such a device. A ground connection also has to be made between the device's signal ground and one of the parallel port's ground pins. The translators used on our demo machine, however, are optically coupled. This means that the translator uses a light-emitting diode, or LED, to transfer the signal that it receives to its internal circuit. Control is accomplished as the signal either lights or extinguishes the LED in the optical coupler. LEDs are activated by current, and so it is generally unreliable to depend on the parallel port output to provide enough current for the optical couplers. Our demo machine uses a 5-volt power supply to provide the current. When the output pin goes to 0 volts, the LED in the optical coupler is lit. When the output pin is 5 volts, the LED is extinguished. The spindle on our demo machine is a small, inexpensive 3.8 amp trimmer, very simply turned on and off for demonstration purposes. An optically isolated solid-state relay turns the motor on and off depending on the state of an output pin. When 0 is written to the output, forcing the pin to 0 volts, the LED within the optical coupler lights and the relay turns the spindle on. When 1 is written to the output, making the output pin 5 volts, no current passes through the LED, the relay opens and the spindle motor stops. When choosing a solid-state relay for a highly inductive load like a spindle motor, it is important to make sure that it is a zero-crossing type. Zero-crossing relays have internal sensing which disconnects the load at a time within the 60-cycle wave where it will not produce an inductive voltage spike that might damage the device. The purpose of this demo is just to show how the computer can turn a spindle on and off. It may be more desirable, for safety's sake, for some machines to require a sequence of operations and/or dependence on a latching relay circuit to assure certain controls are not activated at an unexpected time. Since the state of the output pin cannot be controlled until the software actually assumes control over the computer, I am careful to make sure that the AC power to my spindle is off when I power up the demo machine. G-code controller allows you to design an initializing sequence that automatically executes when the software loads. In our demo, we are simply making sure that our spindle output control pin is 5 volts, the state that keeps the spindle motor off. G-code scripts typically use MO3 to turn a spindle on and MO5 to turn a spindle off. Configuration dialogues in the G-code controller application program translate M-codes into sequences of index or LPT commands. For the purpose of our demonstration, only 1 or 2 index or LPT commands are needed. MO3 uses reduced current C0 to turn the spindle on in sequence with a time delay of 1 second to make sure that the spindle is up to speed. MO5 uses reduced current C1 to turn the spindle off. G-code controller's instant block dialog lets us manually turn the spindle on and off using these M-codes. Here is a simple part program that turns the spindle on, plunges the Z stage, traverses a square, then retracts the Z stage and turns the spindle off. Some types of machines, such as machines designed to spray or deposit coatings, require an activation to occur at a particular spot in the tool path, while the tool carriage is in motion and after it has accelerated to vector speed. Index or LPT has this capability, which is utilized by G-code controller. This demo emulates a spraying operation over the path of an arc, where the spray apparatus needs to be activated and deactivated at exact locations along the arc. MO9 is customized to turn on a LED, emulating activation of a spray mechanism. M10 is customized to turn off the LED, emulating its deactivation. Now that we've introduced some factors relating to motion control and digital input and output, it's time to concentrate more on how these things are made available to the human operator by the application program, which is the topic of the next session in this series.